So we're going to go through this exam, so I'm going to write it, and so hopefully you'll be able to see my thought process as we go along with some of the questions. Okay, so true or false, the way that you want to do true or false is you want to, if it's true, the entire statement and everything about it has to be true. If it's false, generally there needs to be one term that you could change or remove or add a different word and it would become true. So I always like to do that, so I'll give you examples as we go along. So I'll read these. An ion is created by adding or subtracting a proton from an atom. So that's not protons, it's electrons. So adding or removing protons would change the element of an atom. So you could either change this to electrons or really you couldn't change ion. It would be electron. Would be make it, so this is false because of the proton. Temperature is intensive, so this is independent. Quantity, that's correct. You can have a cup of water or a pool of water at the same temperature is independent of how much of the water you have. That's a definition of intensive quantity. Isotopes have the same number of protons, but the different number of neutrons. That's true. That's a definition of an isotope. Next one is electrons cannot be accurately described using classical theory. That's true, which is based on the observations made in the macroscopic world. So this is true. So electrons, based up before electrons and subatomic particles were being discovered, classical mechanics was able to describe every observation that was seen in the world, but very small things did not obey these rules, and new rules had to be made, which was quantum mechanics. The next one is milk is a pure substance. So milk is a mixture of multiple components that are in a homogeneous solution, hopefully. So a pure substance would be something like an element or compound. So milk is not a pure substance. It is a homogeneous mixture, again, unless it's spoiled, and then it would be heterogeneous, and that's gross. Next is the Heisenberg uncertainty principle states that you cannot know the position or velocity of an electron exactly. That is correct. So another way to say that is there's no uncertainty in the measurement. So Heisenberg says you have to have uncertainty in the measurement. You can't know the position of it exactly. So that's a true statement. The next one is dry ice subliming. So subliming is going from solid phase to the gas phase. Both physical change is a physical process. That's true. Cooking an egg is a chemical process. That's also true because we are chemically changing the egg structure. We're denaturing the proteins. But you don't need to know that. You just need to know that you can't uncook an egg. It is not a reversible process. Number two, a substance with visibly distinct phases. So visibly distinct is a heterogeneous solution. So we already know that this is not it, this is not it. And heterogeneous solutions can be separated using a physical process. So it's C. Or 5, a substance with uniform composition that can be broken down into elements by chemical process. So again, broken down by chemical process, we know can't be a solution. It has to be, or a mixture. So that only actually leaves B, but let's make sure that's right. So a compound can be broken down by a chemical process into elements. That's actually the definition of a compound, so that makes sense. Next one. Using a series of ions. So for each one of these, we're going to select whatever it says. So in all cases, they're greatest. So number of electrons. Okay, so this one is actually a little bit of work. So I'm going to grab a calculator. So I'm going to have it handy. And a periodic table, which I have here as well. Okay, so the periodic table is the first thing I'm going to do. I'm going to label all of the protons for these compounds. So I'm going to find nickel, and nickel has 28 protons. I'm going to put that there. So 28, 28, 28. Chlorine has 17. Iron has 26. And cobalt has 27. So the first thing you want to do is put down the number of protons. And so that actually is the easiest. Let's go down to number of protons. This is easy because I just labeled them. We know that nickel has 28. That is the largest amount. Now, number of electrons is going to be the number of protons in either plus the charge for negative minus the charge for positive ions. So I'm going to look at, okay, the number of protons that has the most is, so I'm not going to look at chlorine here because I know that 17, there's no charges that great to actually make it as big as 26, 27, or 28. So 28 neutrons, that's going to give me 28 minus 2 because we've lost 2 electrons. That's 26 electrons. Chlorine is 18 electrons. Iron 2 plus is 24 electrons, and cobalt 2 plus is 25 electrons. So we see here that nickel, even though it lost 2, is going to have 1 more than cobalt. So that's there. And then for neutrons, we're looking at, so we'll do that down here. So number of neutrons is 46 minus 28. So 46 minus 28 is 18. So we have 18 neutrons here. 17 minus 35. So that's 18 as well. 26. So we have 54 minus 26 is 54 minus 26 is 28. So 54 minus 26 is 28. That seems to be in the lead so far. And then cobalt, we have 54 minus 27. So that's subtracting 1 more. So this is 28. So this would be 27. So we can see that that's probably the trickiest one. So this is 28. So that's going to be the highest number of neutrons. Now that's a pretty. Now I just want to point out here that this is actually was a lot of work. It took way longer than the other questions, and it was worth more points. So, and look at all the stuff I wrote out. So hopefully you have also written out as much of these notes. This is how I do this if I were trying to figure it out. So just pointing that out, that you should be writing out all this stuff as well, using a calculator if you're not sure. Okay. Now to calculate the weighted percent of forestium. So a weighted average is going to be taking the percentages and multiplying it by the atomic mass. So the weighted average is going to be equal to the contribution. So we'll do this first and this second. So you take 0.36, that's the percentage, and you multiply it by the mass of what you have of that. It's 104.00 AMU plus 0.64 times 106 AMU. And so if you do this, you can, and I'm just going to use parentheses, so I'm going to do 0.36 times 104, and then again, I don't need to put the zeros in because they won't change the number, and then plus, careful to do a plus there, 0.64 times 106. I like to use a graphing calculator because I can see the numbers I have. Now, I'm going to hit enter, and I know I did it right because the number should be between 104 and 106, and I get 105.28. Again, 2 decimal places here, so I'm going to report 2, and this is AMU, because that's the units we're given there. So that would be our answer. Okay. Next problem is going to be completing this table. So we can start off with the aluminum and go from there. So let's just start off with number of protons is 13. Number of neutrons is 28 minus 13. So that's 15. Number of electrons is going to be 13 as protons, but we have lost 3 electrons because it is a positive charge, so that's equal to 10. atomic number is the same as the number of protons. That's 13. That's just testing to see if you know what atomic number is. Mass number is the number of protons plus electrons, which is this top number right here. This is a mass number. And then net charge is going to be plus 3 or 3 plus. It really does not matter which one you use, so that either one's fine. So now we have to do the symbol for the second column. So we know the number. I need to tell you the number of protons. So the number of protons is 34. So I go to the periodic table. I look up 34. Oh, I've gone way too far. I look up 34 on the periodic table, and I see that that's selenium. And then I'm going to put the rest of the numbers down as well. So I know this is 34. Number of electrons are not provided. Let's see, number of neutrons. Oh, net charge is 0. So if the net charge is 0, it means the same number of protons as neutrons. Same number of protons as electrons. So that has to be 34. And then the atomic number is 34. Mass number is neutrons plus protons, so 34 plus 46 is going to be 80. And so I'll put that up here. If you have a net charge of 0, you don't need to put anything for the charge. You just leave it like that. Okay. Now this next bigger than smaller, you'll see it's 12 points, and so each one of these is like a mini problem. So just be aware of that. So, okay, for the first one, I know that 6.022 times 10 to the 23rd of anything is equal to 1 mole. So if I have 2.02 times 10 to the 23rd, this is not even half a mole. This is like 1/3 of a mole, because 1 mole is 6 point something. So if you have 2 point something, that's 1/3 of that number, and this is the same, times 10 to the 23. So this is, I always like to just remind myself, okay, so this is bigger, and the way these read is that 0.5 moles is bigger than this. So make sure you read that right, so you get it so you don't flip them. Number of neutrons in phosphorus. So we have to look at the protons in phosphorus. Phosphorus has 15. So we have 17. So this is 17 neutrons. Oop. Okay, and then number of neutrons in silicon. So silicon has 14. So that is 18 neutrons. So there is smaller number of neutrons in phosphorus 32 is smaller than the number of neutrons, because there's one more neutron in silicon 32. So if we look at the short history, or the scale of the universe, we see that a human egg is bigger than a bacteria by a good amount. And then the mass of a neutron and mass of a proton, those are the same in size, both very small. Okay. Next is converting the following measurements. So we're going to use our different conversions. So I'm going to write these onto the right. So I'm going to start off what we have, 124 milliliters, and I want to get rid of milliliters. I want to go to liters, so I'm going to put milliliters on the bottom, liters on the top. I know there are 1,000 milliliters in 1 liter, so milliliters cancel. And so I'm going to divide this by 1,000, which is going to be 0.124 liters, 0.124. The next is kilograms to grams, so again I start out with 0.00350 kilograms, and I want to go to grams. So I know that I should have a bigger number because I'm going from a big unit to a small unit. So kilograms on bottom, and then grams on top. I know there's 1,000 grams. I'm going to multiply this by 1,000, and so really what I'm doing is I'm moving this 3 decimal places. And so I get 3.50 grams. 3.50. Next is nanometers to millimeters. So this is the one where we have to do 2 steps. So we start off with, I'm going to do it down here because we're going to do one more step, 19 nanometers. And then we're going to multiply that by a conversion factor of nanometers. I'm going to go back to meters. You can be fancy and go right to millimeters. That's fine, but you don't need to be fancy. I want to be right. So I know that in 1 meter, there's 1 times 10 to the positive 9 nanometers. So nanometers cancel, and then if I want to go from meters to millimeters, I know in 1 meter there is 1,000 millimeters. So if we get the answer to that, so we see here that this is 1,000. So well, we can put this in our calculator. That's fine. So I'm going to do 19,000. That's 19 times 1,000 divided by 1 second EE, or E in this case, 9. So I have 1E9. So this on my calculator looks like 1E9. So make sure that you have been using that correctly. And so you get basically 9 minus 3, so that gives you -6, and 19, so that gives 1.9 to the -5. So we have that here, equals 1.9 times 10 to the -5, and we want millimeters. So this is 1.9 times 10 to the -5. And then the last one is we have 1.35 times 10 to the 9 liters times, going to get rid of liters, get gigaliters. I know that in 1 gigaliter, there is 1 times 10 to the positive 9 liters. So it's a lot. It's very similar to nanometers and meters, but we're going the other way. So we would expect, in this case, that it should be a smaller number than a really big one we have. So liters cancel. So I have, if I divide by times 10 to the 9, this goes away and this goes away. So I just multiply 1.35. So I'm left with, I don't really need my calculator, 1.35 gigaliters. So 1.35. Those are conversions. And let's see. We are missing, oh, there they are. So I don't know why they got skipped over to the back, but anyway, that's weird. Okay, but here we go. So this is 11. Okay, that's interesting. All right. So we got here, I'll do this in black. Circle all of the objects that carbon-14 dating would be an appropriate method to determine the age range. So carbon-14 is good between 1,000 and we say 60,000 years is where we want to go. You can push it up beyond that, but so definitely not a million years. So we can do this and this. A petrified wood, this is beyond the scope of what's accurate. An appropriate method, we wouldn't really use that, and so definitely B and C. If you put D, you know, it's just that there isn't that much carbon-14 left. It would be very hard to not have contamination of other samples, and so we really say that, you know, 20,000 is really where we're feeling pretty accurate. You can push it to 60,000, 80,000 would not be an appropriate method. Okay, for number 9, the Johnny. So we're just doing a conversion here. So I'm gonna convert both of these to liters and compare them. So I'm gonna start with Johnny's. So we're gonna see who has more. So 5.5 times 10 to the 3 milliliters times milliliters on bottom, liters on top. 1,000 milliliters in 1 liter. 1,000 is times 10 to the 3, so that's 5.5 liters for Johnny. This is Johnny. And then for Sally, she has 11 times 10 to the 8 nanoliters. And so I know that, okay, we have nanoliters on bottom, liters on top. In 1 liter, there is 1 times 10 to the 9 nanoliters. So I'm actually going to make this, so that's 1.1 liters, because the 9 and the 8, we're going to have to move this decimal place 1. That's Sally. So who has more, the question is, who has more water? Johnny does. Okay, and the last question has to do with dimensional analysis. So if we start off with a 0.895 gram sample of compound, and I want to figure out how many molecules, I need to first go to moles. So I use the molecular weight, where this 45 stays with the grams. So I'm going to put grams and moles. And 1 mole, they tell us it's 45.799 grams. Cancel. We have a mole. Use Avogadro's number in. So we have mole and molecules. In 1 mole, there is 6.022 times 10 to the 23rd. Moles cancel, molecules is what we have there, and then we're good. So I'm going to take this and do parentheses, 0.895 multiplied by Avogadro's number, 6.022, and then do that E, and just put 23rd positive, end parentheses, divided by 45.799, and I get a big number, 1.176 times 10 to the 22nd molecules. Again, it should be a big number, not very small. And so we have 3, that's fine, we'll just do that. Okay, and that is it.